Well, good afternoon, ladies and gentlemen. I'm sorry about that. I think was positive feedback on my end. Sorted now. All right, so I want us to begin our study. We are going to carry on looking at state space representation. More specifically, we have been looking at the method of trying to represent any control system as a state space. That means we represent the system based on state equations and the output equation. So we did that for a couple of systems in the previous classes, but we want to move further ahead and see how we can convert a transfer function to a state space and vice versa. You see, one of the things that happens, especially when you are simulating physical systems in digital computers, is that you might be represented or you might be given a transfer function, but you cannot use the transfer function directly in your simulation of the physical system in a computer. So what you have to do is convert that transfer function first into state space representation. Once you do that, then you're able to represent that system for simulation using a digital tool. So we have to find techniques of representing transfer functions as state space, and also vice versa. The reason is usually computers will, of course, like we had said previously, will use state space representation, but we as designers or as human beings, we tend to represent systems more often using transfer functions, because those transfer functions give us the relation between the input and the output. So it's a quick way of analyzing the relationship between the input and the output of a physical system. But computers would probably understand that system when presented with state space representation. Now, we have been talking about state variables. Now, we agreed that you have to come up with state variables whenever you are representing your system as state equations. You have to come up with state variables. I just wanted to mention that certain times the state variables are also called phase variables. So let me share my screen so that we can proceed with converting a transfer function to state space. Now, because I have already presented or supplied you with notes on this, what I will do is try as much as possible to avoid the examples that you have in your notes. Those are left for you to read and understand. So I will try and make use of examples that are not in your notes, because those are the examples that probably would widen your scope. So you will use the notes to help you, but as a supplementary, I'll provide other examples that we can use in our analysis. So there are basically procedures or steps that we must follow in order to convert a transfer function into a state space representation. Then later, maybe in the next class, we'll look at the reverse. So there are two types of transfer functions that we need to convert. So you might have a transfer function C of S over R of S. You have the notes, ladies and gentlemen, and you have examples. So I'll also just be giving my own other examples. There are two types of transfer functions that can be converted into state space representation, but each one has its own way. That's why we have to know which types of transfer functions you're dealing with. The first transfer function is one in which the numerator term is a constant and the denominator term is, of course, a polynomial. The other transfer function is one in which both the numerator term and the denominator term are polynomials, okay? So the process of converting these type of transfer functions are slightly different, So we shall start with the first technique, and then I'll develop it into the second technique, and I'll use one example to illustrate what I'm talking about so that there's continuity. More examples and even exercises are available in your notes for your own study. So for example, in fact, let me use an example that appeared in an exam paper. Good, that's what I'll do. So let's start with converting the first system. So let's talk about system with a constant term in the numerator, okay? So converting a transfer function with a constant term in the numerator. So we are looking at the first type of example. So example, so the question would be, find state space representation, find the state space representation in phase variable. When we talk about phase variable, I've told you, let me just put it even in brackets. Of course, the question would not be given to you like this, but this is like state variables. When we talk about phase variable form, it just consists of state variables, okay? Okay, so for the transfer function, in the figure below, and so we have the transfer function here. This is a feed forward transfer function that's given, but anyway, we can get the, so this is provided as the input C of S, and I think the input is always R of S. For uniformity, I'll use R of S, and I'll use this as C of S. And the transfer function we are given here is, let me just use a simple one, 1 over S squared plus 13S plus 16. Okay, so it's a simple transfer function that we are required to convert into state space representation or in phase variable form. Okay, that is making use of state variables. Okay, so that's what we are required to do. Now, like I've said, and you expected to study this also as you carry along, is you have to follow a few steps. They're very simple, but they'll guide you into the solution, and you can do it very fast. So, for example, in our case here, because it's a very simple example, the first thing you have to do is you have to write the differential equation, okay? And then you write your, so let me just say, write the transfer function in differential equation form. So clearly we can see from our case here that C of S over R of S is the same as 1 over s squared plus 13s plus 16. Please note that in our case, this is the first case where the numerator term is a constant. It can be any value as long as it's a constant. So this process helps us when we are writing it as a constant. So how do you write a transfer function in differential form? Or how do you come up with a differential equation from your transfer function? It's always very easy. First, you linearize this system, that is, you cross multiply. And so if I cross multiply this, we'll have a system like s squared plus 13s plus 16 into C of S equals to R of S. Okay? Once you have it like that, then you take inverse Laplace transforms. And of course, because inverse Laplace transforms require initial conditions, ours will assume zero initial conditions. Okay? So from here, basically, we apply inverse Laplace transforms, assuming zero initial conditions. To just simplify the process. So if you apply your inverse Laplace transforms, meaning we convert this now, because you can see this is in the frequency domain. So that's why we are applying inverse Laplace, so that we get them in time domain. So in our equation here, we can quickly do that, because it's a very simple second order system. You can have a third order, you can have as many orders as you want, and those also appear in your notes, so I'm not worried about it. I'm just doing a simple one to illustrate the whole thing. So let's convert this. So we know that if we convert, this is s squared. So to convert it into time domain, it's a double derivative because it's second order, plus you've got the I'm using t. I shouldn't use t. Ladies and gentlemen, I should use c because it's small c. Should use small c because I'm converting. I'm doing inverse Laplace transform, so I'm just converting into small c, and then 13s squared would just be 13 small s. Of course, sorry. I've done this long time ago, so now it's I keep confusing. So it's a small c, 13c, as a derivative plus 16 c should be equal to r. So remember, we can as well write this as what we mean. It's now a function of time. So I'm just avoiding writing the t because it's a function of time, yes. So it's known. It's only that it will take. So there's no harm whether you write it in this form or in this form. It's the same thing, okay? Only that, sometimes it becomes too tedious to keep repeating. We know that you're doing inverse Laplace transform, so you're writing as a function of time, okay? Now, remember, don't forget, the idea is we are converting a transfer function into phase variable form, meaning we want to convert it in form of state variables. So if you want to convert the system in form of state variables, we need to identify what those state variables are. What are the state variables in this case? So usually, maybe I should say that should be our step 2. Step 2. So step 2 is where you select your state variables. You select state variables. And we had agreed previously that the rule of thumb is 1, the number of state variables should correspond to the order of your differential equation. In our case, we have a second order differential equation, so we only expect 2 state variables, meaning 2 state variables are sufficient to completely describe the system. So the other rule of thumb was that the state variables are chosen such that you choose a physical variable with its derivative. So you choose a state variable and its successive derivatives. And the number that you choose would depend on the order of the differential equation. So in our case, we have a second order differential equations. So we need two state variables. So you can always just say, let the state variables be x1 and x2, because they are supposed to be two. Now, what is x1 based on what is the physical variable we are picking based on our differential equation? So you can say x1 should be equal to, you can pick a clue of what your first state variable is, because it is a variable that has corresponding derivatives. So if you look at your the differential equation, pick the variable that has derivatives. That's the idea of knowing what state variables are that you need to pick. So in our case here, you see C is the variable that has derivatives. So we are going to pick x1 as C, and then we are going to pick x2 as its derivative. So x2 is going to be the derivative of C. If it was a third order, then x3 would be the double derivative of C, and so on and so forth. So it's always easy to pick that out based on your differential equation. You can tell what variable has its derivatives, and that becomes your state variable. So in our case, we have picked our state variable as C and the derivative of C from the equations that we have. Now, because now we are almost done, remember, the idea is simply to convert a transfer function into state equations and the output equation. So clearly, you can see from our choice of the state variables that if I differentiate, I'm going to make this easy. So let me say, if I differentiate, let me just say differentiation. Okay. So if I differentiate the first state variable, meaning if I get the derivative of x1, it is the same as getting the derivative of C. But the derivative of C from the second state variable is the same as x2. Okay. And if I get the derivative of x2, the second state variable, it's the same as getting the double derivative of C, meaning I get the derivative on the left-hand side, get the derivative on the right-hand side. But what is the equivalent of the double derivative of C in terms of the input? So you come back and look at your equation here, and you will see that we can make the double derivative of C the subject of the formula, so that we are able to write everything in terms of x1, x2, because those are our state variables. And of course, the input, R. The input for our case here is R. But we don't want to use C. We want to use x1 and x2. Those are our choices of state variables. So that's why the first derivative x1 has already been written in terms of x2, so we can use that. Then the second one, getting the derivative of x2, it's double derivative of C. Now, the double derivative of C, if we make C the subject, the double derivative of C, this one here, the subject of the formula, we are going to have minus 13, let me do it the long way so that it's visible for everyone, minus 13 derivative, because I'm taking everything to the other side, minus 16, minus 16 C, okay, plus R. But remember, I'm trying to avoid the C's. I want all my equations to be written in terms of x1 and x2. So this is easy because I know this is the same as minus 13. Then I just come and see what is C derivative. That is x2. So I'll write this as x2 minus 16. What is C? C is x1. Of course, plus R. So now finally you have a equation in such a way that you have x2 derivative should be equal to minus 13. Let me write it properly now in order. Minus 16 minus 16 x1. I'm reordering minus 13 x2 plus R. So ladies and gentlemen, if you remember, the idea was you have to get something in the form of x equal to ax plus b, the state variables. So in our case here, it is x1, x2 should be something here. Then you have the state matrix, x1, x2. Of course, this is dot and this is derivative. Plus, of course, you see the input matrix. So you can see that's what I'm trying to do. That is exactly what I'm trying to do. So that now I see on the left hand side, I have x1 derivative and x2 derivative. On the right hand side, I also have x1 and x2, and of course the input. So that makes it easy because that's exactly the representation that we have for state equations and also for the output equation. So now once I have done it like this, then you can now write your state equation. So step 3. Very simple step. So let me just write step 3 here. Step 3, we now write state equations. So in our case here, you can see writing state equations will be x1 derivative, x2 derivative. That's on the left hand side. Then on the right hand side, we can see what corresponds to x1 because we now have this equation. I'm using this equation 1 and this as equation 2. So you can see that for x1, the corresponding element there is 0. Because x2, the corresponding, the coefficient of x2 is 1. For the second case, the coefficient of x1 is minus 16, and the coefficient of x2 is minus 13. So x1, x2, like that. Of course, we have R, so we have to add it. And R does not appear in the first equation. It only appears in the second equation, and its coefficient is 1. So then we make that equal to R. Please remember that even R in itself is a vector. So we are having the typical equation that we said was the representation, the state equation. So this is A, this is X plus, of course, this is B. Okay, it's not a matrix, it's a vector, but it's a, okay, I would say it's a 2x1 matrix. So it's still fine. So that is the general equation for the state equation. But remember, ladies and gentlemen, it's not complete until we have the output equation. State space representation is never complete until we have the output equation. So the output equation, once you have you're able to obtain the other equations, the output equation is always very easy to write, because remember, the output equation should be in the form of y. In this case, okay, we'll see what our y is. Y is equal to cx plus d. Okay, mostly this D is 0. Okay, you'll see that most equations, the D is just 0. So Y is, so we need to write something in terms of Y equals to the output matrix, and then of course the X1 and X2 are included. So in our case, you simply come back to your equation here and see what we had written here. I want to make it very easy, where we had indicated that Y, we can write somewhere here that Y, which is the output, let me just write it somewhere here, Y, which is the output, should be equal to C which is equal to X1. Because, ladies and gentlemen, it's very simple. I'm not. So the output clearly from the diagram is C. Okay, that's why I'm saying here that Y, which is the output, in our case is represented as C. But C, if you look at our state variable choice, is the same as X1. Okay, so now you have this to form your output equation, that C equals to X1. So you can actually just write that Y, which we have just said is the same as C, should be equal to the, you need a matrix, but you also have X1 and X2 because we have to write it in state variable form. So, sorry, let me just make it easy. So you need a matrix there, and then you have X1, X2. Of course, we don't have a D because we just said Y equals to C, which is equal to X1. So writing this in a vector form, you can see that Y equals to C. So the coefficient of X1 is 1. The coefficient of X2 is 0. So this becomes your output equation. So this is the output equation. Output equation. And that marks the end of our state space representation. So remember, we began with a transfer function C of S over R of S. Over time, we decided to first convert it into a differential equation format. Once we have it in differential equation format, then we pick the state variables from that differential equation. Based on the order, we know that there are 2 in this case, and we pick the variable that has derivatives. So we have picked C and the derivative of C because they are available in our differential equation. And then we do a little bit of differentiation or manipulation, because the reason we are doing this differentiation is because our equation demands that the state equation demands that the terms on the left-hand side be a derivative of your variables, of your state variables. So that's why we had to differentiate here, because our variables are X1 and X2. So we have to differentiate to get X1 derivative and X2 derivative, because that is the format of the state equation. That's why the differentiation needed to be done. And then on the right-hand side, we just make sure that we convert all the terms in the form of X1 and X2, in the form of the state variables. And then you form your matrix equations, and you are home and dry. So that is the way we convert a system that has a constant in the numerator, a transfer function that has a constant in the numerator. That is how we convert it into a state representation form. So let me do the last one, which again is now, how about a transfer function that has got a polynomial both in the numerator and in the denominator, because that also requires a procedure. It's not very different from what we have done. There's just a slight variation, which is critical, which we must also learn about. Again, an example is available in your notes. so I will not do that example in your notes. I will carry on with the example that I have here in the that we are already doing in class today. So let me just write another example. So here we now want to do conversion. Let me just check the time. Okay, so I can do it in the next 15 minutes, then we finish up. Okay, so how about converting transfer function that has got a polynomial both in the numerator and in the denominator? That's very important. So conversion of a transfer function with a polynomial in S in the numerator. That's another one. How do we do this? Now, it's a very, very simple process. All you have to do is know how to proceed, and then the whole thing will just be easy. So step one, so let me write the example. In fact, let me copy it from the exam itself. I like solving the exam question papers because a lot of you students keep sending me questions that they draw from those past papers. So I will write how it is written there. It states that find okay, the state equations and output equation for the phase variable representation of the transfer function and the transfer function here is given as g of s equal to 5s plus 1. So you can see that the numerator is not a constant now. It has a polynomial in s, so s squared plus 13s plus 16. Good. And it's a good 6 marks. Okay, so now we have to find a way of converting this transfer function into state space representation, but taking note of the fact that the numerator is not a constant like in the previous case. So here, whenever the numerator is a polynomial in S, the first step is to separate the system. So separate G of S into two cascaded blocks. Very important because this is basically the difference. Okay, with the first block, and the order is very important, with the first block containing the denominator. Very important. With the first block containing the denominator, and the second block, containing the numerator. That order is critical because if you don't do it in that order, you will never get the question correct. What I mean is this, because some people probably understand best when it's illustrated. What I mean is this: our G of S here is simply is simply C of S over R of S. Okay, so as it is, our transfer function is of this form. Our G of S, that is of this form, where you've got your R of S, and it is 5S plus 1 over S squared plus 13S plus 16, and this is C of S. So once we have discovered that the numerator of our transfer function is a polynomial in S, then the rule says that we have to cascade those blocks into two main blocks. We have to cascade it. So now you still have your R of S here, and you still have your C of S there. But now you must have, remember, the denominator term takes the first block. So the denominator term takes the first block, S squared plus 13S plus 16. And the numerator term takes the second block. That is the order. Very critical. So the second block is 5S plus 1. Okay, so it is the same system, it's just cascaded. So if you were to draw this back into a single block, of course, you see it's equivalent. But now for easy manipulation, we have to introduce a term here. Let me just call it T of S, so that now we are able to refer to the first block as a transfer function and also refer to the second block as a transfer function. It can be T of S, you can put any value, you can put X of S, it doesn't have to be T, it can be X of S, whatever you want, whatever term you decide to use, as long as you're consistent with it. So now it becomes easy to again use the techniques that we had to carry on and solve this. So because in step 1 you have cascaded, then step 2 now, I told you it's just slightly different from the previous one. Step 2 now in this case is you have to get the state equations. So let me just say, find state equations for the first block. Okay? So you must get the equations for the first block. Now, to do that, remember, it's just like saying I have given you a system where you have 1 over S squared plus 13S plus 16. And here you have T of S, and here you have R of S. So you have to go the long way, just like I did, but we've done the example, we've done it up here, but because I don't want to jump or skip things, you can now say, because now you know the process, so you can say T of S over R of S equal to 1 over S squared plus 13S plus 16. Very simple. Okay? And if we linearize, we are going to have S squared plus 13S plus 16 T of S to be equal to R of S. In this case, now you can see that if we get the inverse Laplace transforms, I'm not writing the information now because it's like the previous example we did. So if we get the inverse Laplace transforms, we'll have double derivative of T plus 13 derivative of T plus 16T equal to R. And then, of course, we pick our state variables, just like we did in the previous case. And the state variables are x1 and x2 because it's second order. And x1 in this case is just going to be equal to t. We pick variables that have derivatives. So x2 is going to be its derivative, like that. Okay? If you differentiate those derivatives, you will have x1 derivative should be equal to, of course, t derivative, which is the same as x2. just like we did the previous case. X2 derivative should be equal to minus 13 x2 minus 16 x1 plus r. Okay, and so you come up with your state equations. I'm doing this quickly now because we've done a similar example. It's only that now this is a cascaded system. So it's a two-part way. So the state equation becomes x1, x2, derivative like that, should be equal to, we found it to be 0, 1. I think it was minus 16, 13. Minus 16, 13. Minus 16, minus 13, like that, of x1, x2, like that, plus 0, 1 of r. So, ladies and gentlemen, you can see that what I have done here is, one, I cascaded the transfer function into two blocks. The denominator takes the first block, then the numerator takes the second block. Then I forget about the second block for a moment and only get the state equations for the first block. So you can, that's why you see I'm only concerned with the first block. I've forgotten about the second block just for a moment so that I get the state equations. So this method, the clue here, or the point to note, yes, the point to note here is that for a system that has got a polynomial in the numerator, yeah, let me just write, for a system with a polynomial, when I say a system, I mean a transfer function, okay, with a polynomial in S in the numerator, the state equations are obtained from the first block. And the first block is the one that contains the denominator term. I hope that is very clear. When you have a system or a transfer function that has got a polynomial in S in the numerator, you draw your state equations from the first block where you had your denominator term. So that's why the state equations for our system is this. And how did we get it? From the denominator term, which is the first block. That's how we obtain it. Then the output equation is obtained from the second block. So let me continue. The output equation is obtained from the second block, the second cascaded block, and that is the one that containing the numerator term. That is the rule. So it means, therefore, that I have to now, to go, because now we have the state equations, but we don't have the output equation. So the output equation, we have to obtain it from the second block. And you can see that the second block is this. This is T of S, and this is C of S, and you have 5S plus 1. I hope so. Let me confirm. 5S plus 1, yeah. So this is where you obtain your output equation from, but this is where you obtain your input equation, the state equations from. So let's obtain the output equation from this. So it means we have to write the transfer function C of S now over T of S should be equal to 5S plus 1. The beauty with this is it's easier. We obtain everything. Our choice of state variables for this part of the equation is based on the state variables that we already picked when we were dealing with the first block, such that you don't get different state variables for the first block and another set of state variables for the second block. The second block for the output equation has the same state variables, because the variables need to be similar, because this is one system. It's only we who cascaded them for ease of manipulation. So now from here, if we make this, we linearize this, you can see that we'll have C of S should be equal to 5S plus 1 T of S. Notice we are now on the second block, and the second block, we want to use it to obtain the output equation. We've already obtained state equations from the first block. This one is even easier because a lot of steps are now. So if you get the inverse Laplace transforms, ladies and gentlemen, it's small c of t should be equal to, this should just be 5t derivative because it's s plus t. Okay. It's very easy because it's just like the first manipulation. Now, here, in this case, you just look at your equation and you ask yourself, from the differential equation, is my equation first order, second order, or third order? Clearly, it's visible from the differential equation that this is a first order. It's 5s plus 1. So the differential equation is derivative of 5 of t plus t. So it's first order, meaning you only need the first state variable. Meaning that state variable, we say x1 just like we said previously, but now here we don't have two state variables, we just have one. So we only pick it as t. If we had two, if the numerator polynomial had was a second order, then we would have that. But in our case, we only have first order, so we simply pick the variable that has derivatives. So it's just x1 equals to t. So if I get the derivative of x1, so differentiation, remember we were doing differentiation because that is what the equations usually want us to do. So x1 differentiated is just the same as differentiating t. But if you differentiate t, what is the differential of t even from the first? You can see if you differentiate x1, it's like differentiating t and you get x2. So you write x2 here. So notice we've obtained it from what the equation we already had here previously, that if you differentiate x1, you get the derivative of t, and of course, and that is the same as x2. So that's the same thing that I have done here. And then now it makes it easy because the output of your equation here, you can see the output of your equation, you can come to the original equation, the output y should be c, because c is the output, c of s. So the output is, our output y is c, because remember the equation usually says that the output equation is y equals to c of x plus d. Okay, so if you remember that, so our y in this case is c of t, okay, or a small c, okay, and it's the same as, you can, c of t is here, you can see y is c, and what is c of t? It is the same as 5 derivative of t plus t, but we need this in terms of x1 and x2. So derivative of t is x2, so we just have 5 of x2, and derivative, t itself is x1. So that we have it in terms of x1 and x2. And therefore here, y, which is equals to c, should be equal to, we can see that we need to write it in terms of a matrix there, or a vector, but it has to be in terms of x1 and x2. So what is the coefficient of x1? It's 1 from our equation there, and the coefficient of x2 is 5. So this becomes our output equation. This is the output equation. Output equation. Okay, so notice that the state equations is obtained from the first block, then the output equations are obtained, the output equation is obtained from the second block, but the process is the same. As long as you know that you're converting your transfer function into differential format, you get your state variables, and then you make sure that you have derivatives on the left-hand side, and then on the right-hand side, you write your equations in terms of the state variables. Then you're home and dry. So basically, that is how you obtain state space representation from transfer functions. And the reason for that is typically systems are represented in the form of transfer functions. But whenever we want to do digital simulation, we're using a computer or a computer tool, we have to convert these transfer functions into state space representation. You see, this is like a matrix. So entering this in MATLAB is easier because we are representing it in terms of matrices. So which can be easily entered in a digital system. And that is why it is necessary to be able to convert from transfer function to state space representation. So ladies and gentlemen, I'll end my class here and wait for the next class where we are going to convert from state space back to transfer function. Because certain times we have state space representation from our simulation, but it's not very easy for human beings to quickly relate the relationship between the input and the output when they read state space representation. But when you convert it back to transfer function, it quickly makes sense for you to know the relationship between the input and the output. So we also have a formula or a procedure for converting from state space to transfer function. That is left for the next class, which should be Monday. Okay? So ladies and gentlemen, I beg to stop sharing and listen for any questions before we close, because we have just 4 minutes. I highly encourage you to attempt the examples that are given in your notes, but also in your notes at the end of each section, there's an exercise where you're asked to solve a similar problem. Also solve those problems. It's for your own advantage. So that's why I'm also trying to avoid the examples that are already available in your notes, and I do those that are not there just to give you a wider perspective to work with. So thank you very much for listening. If there are no questions, then we'll end the class here and we'll meet on Monday morning where we'll do the opposite. Yes, Ismail. Yeah. Oh, okay. No, that's okay. Okay. You see, okay, maybe I've used the term vaguely, but my point is, if you have a system where you have C of X over R of S equals to 10S squared plus 5S plus 2 over 2S cubed plus 3S squared plus 2S plus 4. This system is a transfer function that is a fraction. It's basically a fraction. Linearizing, when I talk about linearization, I simply mean you cross multiply so that you have a system that is only represented in one line, not in terms of fractions. So if you cross multiply this system, you'll see that now you have 2S cubed plus 3S squared plus 2S plus 4 of C of S equals to, now you have 10S squared plus 5S plus 2 of R of S. So this is what I say, the system is now linear, not in, because I understand what you mean, not in to refer to the systems here, because this cannot be a linear system, but we have made the equation linear for us. We are having only one line of equation rather than having this format. because manipulation using this can be a little tedious. But when it's now a linear representation like this, it is not the system that I'm referring to. The system dynamic could still be non-linear, but the manipulation, the mathematical manipulation, is now easier to deal with. That's what I mean. So please, when I say linearization, I'm not saying that you're converting a non-linear system into a linear one. No. It's just the mathematical manipulation. So we are making it into one line, so it's easy to work with. Ismail, sawa sawa? All right. Sawa. Kuna mtu mwingine ako na shida? Okay, I see people are already logging off. Our time is already up. Thank you guys so much for listening. Have a good weekend.